The first entry in here is always the output identifier. And I'll show you an example in just a moment. And then anything else that you put in this port list is interpreted to be an input. Okay? So, as an example, if that was the type of gate that I wanted to put into my circuit, that's how I would declare it in the Verilog code. And you can put in here the optional identifier. We saw in schematics earlier in this course, specifically when we went through that ASIC guide, that it's not uncommon to have some identifier, a U number for a gate. That's where you put it. And seeing as if I'm doing a gate level design to keep track of which gate I'm talking about, I would probably assign a U number to it, and that's what you would put in there when you declare it in the program. Now, it's important you understand that there is no limit on the number of inputs. With two notable exceptions. Which I will cover in just a moment. So I could do the following. That would be the declaration of a 5-input OR gate. Now, if you go to the integrated circuit manufacturers, I doubt very seriously you're going to find a 5-input OR gate sold by a manufacturer. That said, I could still declare it. But the synthesizer could figure out if you had only provided, let's say, 2 and 3 input OR gates in your component library, it could figure out how to synthesize that particular function. Now, what are the two notable exceptions? An inverter. Obviously, an inverter only has one input. What's the other exception? Well, I guess there's 3 exceptions.
It can have multiple outputs.
That's not a true statement. We'll get to that. What's the other 2 exceptions? This is something that always amazes me with 172 students.
Oh, yeah. I feel
There ain't no such thing as a 3-input exclusive OR gate. Exclusive OR gates are only 2 input. Now you could exclusive OR 3 variables, but not in a single gate. You could exclusive OR the first 2, take the output of that, go into a second exclusive OR gate, and then exclusive OR the third variable. But these are only available as 2 input. of course, inverters only have one input. Yes?
So if you ended up putting Verilog, XOR, Y, ABC, like
You probably get a synthesizer error.
Okay, the synthesizer.
You would need to split that out as two statements,
Oh,
if you wanted to exclusive or three variables.
So is there a way to specify how many components module is driving?
How many what?
How many components module is driving? Is there gonna be a difference? So you got an AND gate, there's one C.
You really don't have that much control over what the synthesizer does. We're going to be looking later on in the course at a user's guide for a synthesizer. And there are certain options in there, but that's not one of them. Some of the options, for example, you can specify whether you want finite state machines fully encoded or one-hot encoded. So you have options like that you can tell the synthesizer. But at the gate level, there's not too many options that you have to configure the synthesizer. Okay, so this is example 5-1 in the text, and this just shows you some more examples of how you instantiate these. And again, I want to make the point that these gate primitives are considered at the module level. It's just that you don't have to define them. It's just like in C programming. If you include the math.h library, you don't have to write a routine for the cosine function. It's predefined for you. Well, these gate primitives are predefined in Verilog. Now, let's suppose that I want to have multiple instances of the same gate. There's a couple of ways you could do this. One way is I could put these on separate lines. Or you could declare it on a single line separated by commas. Comma, G2, Y2, A2, B2, comma, and so on, and then terminate the entire expression with a semicolon. So you could do it this way, or you could do it that way. It's whichever you prefer. Now, you need to be aware of the fact that in logic circuits, there are 4 possible logic values. What are they?
1, 0, high impedance, and
And don't care. So table 5-1 shows you the truth table for the gate primitives in Verilog. So let's take, for example, this the OR gate, and they're working here with a 2-input OR gate. So there's all 4 values for one input and the other 4 values for the other input. And you'll notice in here that there are a lot of don't cares. If you look at the AND gate up here, the reason why you have the 0 up here is if one of the inputs is a 0, even if you have a don't care on the other input, you know that the output is going to be 0. For the rest of these, however, they're don't cares. So I'm not expecting that you memorize these truth tables, but be aware of the fact that all 4 values are covered, and what you wind up getting with the high impedance or the don't care is you have the possibility, depending on the gate, of having a don't care for the output. Now, when you simulate, if you have a don't care on an output of a gate, it shows up as just a gray bar equivalent to the crosshatch that you saw in memory chip timing diagrams and so on, where it's not a valid input. And it depends on the simulator how they show the don't care. Okay, so for the buffer and inverter, the gate primitive keyword is buff, B-U-F, for a buffer, and N-O-T, not, for the inverter. Okay, so those are the 2 keywords. And here is the example 5-2 where they show you gate instantiations. These 2 are kind of obvious. N is going to be, again, the first entry is the identifier for the output. So here, out 1 is going to be the output for buffer, and N is the input. If you declare a buffer or a inverter, and the port list has more than 2 entries in it, all of the entries except the last are outputs, so you can have multiple output devices. So this particular device here, or this particular declaration, actually is describing that type of device. Unfortunately, you cannot do one output is complemented, the other one's non-complemented. It'd be nice if you could, but there's no capability of doing it. Yeah.
So, so in my mind, it seems like if you just have one output, I mean, that's a wire or something, you can hook that wire up to multiple devices. Why do you need 2 outputs?
Well, this is just, not saying that you have to use this, this is actually equivalent of 2 buffers, right?
Oh,
In the component library, if all you have is a single input, single output buffer, the synthesizer would take that description and actually create 2 buffers that are operating in parallel. Tri-state buffers. Now, there's 4 possibilities. I can have just a buffer where the control is active high or the control is active low. And similarly, I could have an inverting tri-state buffer where the control is active high or the control is active low. So depending on which one you want, here are the keywords that you would use to instantiate these. And they're actually very easy to remember. Let's take these two. First of all, they're buffers. So it's buff, buff. Now you'll notice after that it says if one, buff if one, buff if zero. That's specifying whether you want the control active high or active low. Buff if one, it's an active high. Buff if zero, your control is active low. And similarly for the NOT gates, you have not if one, not if zero. So you're specifying an inverter, and the if zero or if one determines whether you want an active low or an active high control signal. So down here are a couple of examples. Instantiation of here's a buffer with a active low control signal. And the entries in here are out, the input, and then what identifier you're using for the controller. Okay. I do not believe that you can have multiple outputs on the tri-state buffers. I want to show you a little more sophisticated design. And this is actually an excellent design that your author has chosen, a 4-to-1 multiplexer. And the reason why this is a particularly good example is you're going to encounter this design 2 more times. Because at the end of the next chapter, which covers the data flow level of abstraction, we show how to implement this circuit using data flow. And then in the following chapter, where we get to the behavioral level of abstraction, same design, but we're going to use behavioral code syntax. So you'll see the same design in all 3 levels of abstraction. So this is a multiplexer, 4-to-1. There are 4 inputs, I0, I1, I2, and I3. The output is connected to one of those 4 inputs. Which input is determined by the binary pattern you put on the 2 select inputs. And the function table to the right shows you for various select inputs which input is hooked up to the output. So we want to implement this particular design using the gate level of abstraction. Figure 5-5 in the text shows you the schematic at the gate level to implement that 4-to-1 multiplexer. So let's see, we've got a couple of inverters, we've got 4 3-input AND gates, and we have a 4-input OR gate. Now, before we actually look at the code, I do want to point out one particular thing that you must be mindful of when you're doing gate level designs. We defined previously a net was an interconnection between 2 objects. So there's a lot of nets in here. And each net has to have an identifier. Now, some of the nets already, if you just look at the block itself, already have identifiers. I have 4 inputs identified, so the nets connected there have identifiers. The output, the 4 inputs, and the 2 select lines. Now there are nets internally in here that are not connected to an input or an output. You must give them a label name. You must give them an identifier. It's up to you which identifier you want to use, but you must specify them before you start to do the actual coding. So you'll notice that every net that is not directly connected to an input or the output has got an identifier attached to it. And it's up to you which ones you want to use. And you picked some that kind of make sense. This is S1 for the input to this inverter. The output of the inverter only goes internally to the box. So it needs a label. So the author picked S1N because S1 was in. But you can pick any label that you want. Okay, so we now want to write a Verilog module for that particular circuit. So that's shown down here in example 5-5. So we have module and module. We have to give it a name, so pick MUX4 underbar 2 underbar 1, and there's the port list. Now if you look at the schematic, it was I0, I1, I2, and I3 were inputs, S1 and S0 were inputs, and out was an output. So I need to have 1, 2, 3, 4, 5, 6, 7 entries in the port list. 1, 2, 3, 4, 5, 6, 7. There's the out, I0, I1, I2, I3, S1, and S0. So I've identified what the signals are that will be interfaced to this 4-to-1 multiplexer. But now I have to have the declarations to tell the synthesizer which ones are inputs and which ones are outputs and what size they are. So the port declarations are input I0, I1, I2, I3, and on a separate line, input S1 and S0. Now, it's true that you could have taken the S1 and S0 and put them into a single statement. But I recommend that you not do that and do it the way it's shown. The reason why is I can now add comment lines to document the design. Notice the comments I added here. I1, I0, I2, and I3 are data inputs. Input S1 and S0 are select lines. So if you put them on separate lines, you can document the code as you go along. Now, I have got all of the internal wires, all the internal nets labeled. S1, N, S0N, Y0, Y1, Y2, and Y3. The way you declare those is with the keyword wire. And again, you'll notice that those have been split. So you can add comments if you wish. Okay, so now I have all of my nets defined. I can go ahead and describe the design at the gate level. I have 2 inverters. This inverter has S1 coming in, the output is S1N, not. The output is first, then the input. S1N, comma, S1. S0N, comma, S0. You see how that works? Now I have 4 3-input AND gates. So I have 4 ANDs. Now, they didn't put in the U1, U2, U3. I would have, but your author did not in this example. So here's 4 AND gates. And let's take this AND gate right here. The inputs are I3, S1, and S0. So there's an AND gate that's got Y3 for the output, I3, S1, and S0 for the inputs. It does not matter what order you put these in. You can put them in any order that you want. And then finally you have a 4-input OR gate. The inputs are Y0, Y1, Y2, Y3, and the output is labeled out. So there's your instantiated 4-input OR gate. Out being the identifier for the output, Y0, Y1, Y2, and Y3 for the inputs. Pretty straightforward. This is a valid Verilog module. This can be simulated, this can be synthesized. Let's take a 10-minute break and then I'll come in and show you a couple of other designs.